Okay, so in the previous videos, we have spent a lot of time talking about Lewis dot structures, what they are, the rules for drawing them, and how to draw them, and how they're based upon the valence electrons for the elements in that molecule. What we're going to focus on now is how to use the Lewis dot structure for a molecule to say something about the shape and properties of that molecule. And so to say something about the shape and properties of that molecule, we're obviously going to use the Lewis dot structure, but we're also going to turn to the second bonding theory that Chapter 10 discusses, which is called VSEPR. So VSEPR, it's an abbreviation for valence shell electron pair repulsion theory. What you need to know about VSEPR is essentially that electron groups that are on the central atom help dictate the molecular shape of a molecule. Okay? So if you want to think about these electrons that are around the central atom, electrons are all negatively charged, they repel each other, and when they repel each other, they produce a certain shape, a certain geometry. And that geometry helps dictate some properties of a molecule. So to determine the shape of a molecule with regards to Lewis dot structures in this VSEPR theory, we need to know something about the electron groups, both ones that are bonded to the central atom and lone pairs that are on the central atom. And once we know what electron groups or how many electron groups, bonded and lone pairs that are on the central atom, then we can say something about the shape of that molecule. So, for example, let's look at carbon dioxide. Here is the Lewis dot structure for CO2. If I want to know something about the shape of that molecule, I need to know something about the electron groups, bonding and lone pairs that are attached to the central atom, which in this case is carbon. So to do that, we use something that your book calls and others call an AXE notation, where A, the letter A, denotes your central atom. So in this case, carbon is your central atom, so that would be your A. Then you would look to see how many atoms or how many electron groups are attached to carbon. Now, when looking at electron groups that are bonded, it doesn't matter. It does not matter if they are single or double or triple bonded. It just matters how many there are. So for carbon, I have 1, 2 bonded atoms to carbon. So the way the notation works, they use the letter X to denote the number of electron groups bonded to carbon. And since I have 2 of them, I would call that AX2. AX2 for my VSEPR notation. Now, if I had any lone pairs of electrons on my central atom, then I would denote that with this letter E. If I had just 1 lone pair, it would be E subscript 1. If I had 2, then it would be E subscript 2. This carbon has no lone pairs of electrons on it. Everything that's attached to carbon is bonded via the 2 oxygen atoms. So my VSEPR notation based off of this AXE notation is just AX2. And why is that important? Well, that's important to note because once you know the VSEPR notation from the Lewis dot structure, then you can look up on a chart that I will give you what its molecular geometry or shape is. And as you'll see shortly, all molecules that have an AX2 notation have a linear shape and a particular bond angle. So I can say any molecule with this notation has a linear shape. Let's look at a few more shapes using Vesper notations AX3 and AX4. So this molecule right here would be an example of AX3 notation, where A, my central atom, is carbon. So that would be my A. X, remember, X represents the atom that is bonded to the central atom. Now it doesn't matter, it does not have to be the same atom to determine geometry. You just need to know how many you have. So in this Lewis dot structure on the left, with my central atom, I have 1, 2, 3 bonded atoms. So that would be AX subscript 3. I have no lone pairs of electrons on my central atom. So my Vesper notation would be AX3. And as you'll see shortly, anything that has an AX3 Vesper notation has a molecular shape or a geometry that is trigonal planar. Methane, we did methane or CH4 previously. Here's the Lewis dot structure for methane. My Vesper notation here, my A, my carbon is my central atom. I have 1, 2, 3, 4 bonded atoms to that central atom, so AX4. And anything that is AX4 Vesper notation from the Lewis dot structure has a shape that is tetrahedral. Okay, so those are two examples of molecular shapes, geometries that you will encounter in the Lewis dot structure lab and in the practice problems. But what about lone pairs of electrons? I mentioned when I introduced Vesper that our Vesper notation uses this AXE notation, where E, capital E, represents lone pairs of electrons on the central atom. So let's look at these two Lewis dot structures, carbon dioxide and water. These are the two Lewis dot structures. They both look linear, right? But that's just in 2 dimensions. We need to use our Vesper theory looking at what's attached to the central atom, and that's going to help dictate the shape of the molecule. As we said here with carbon dioxide, this is an AX2 formation. But here with water, considering my oxygen to be the central atom, I have 2 bonded atoms to that oxygen. One is hydrogen, the other is hydrogen as well. But I also have 2 lone pairs of electrons on my central atom that I need to take into account in my Vesper notation. That's where this E subscript 2 comes from. So both of these molecules, they look linear, but they both have different Vesper notations due to the presence of lone pairs. And those lone pairs that are on the central atom, they have to be on the central atom, they change the overall shape of the molecule. So while carbon dioxide, as we said before, AX2 has a linear molecular geometry, those lone pairs change the shape of this molecule to give anything that has an AX2E2 Vesper notation a molecular geometry that is bent. So what I have said is sort of summarized on this chart, and I know this chart looks very busy. I'm going to try and simplify it for you to put it in perspective. So this is the chart that is from your textbook. The most important part of this chart, which obviously you'll be able to use on quizzes and exams, is this section that I'm kind of boxing right here that's on the left-hand side. In this region, this is a way to summarize what the molecular geometry of a molecule is if you know what the Vesper or the AXE notation is for a molecule. So for example, we said anything that has an AX2 Vesper shorthand notation, where A is the central atom, and X represents the atom bonded to the central atom. Anything that's AX2 has a shape that is linear. Things that are AX3 have a shape that is trigonoplanar. And so you can see by looking at the Vesper notation that once you start adding lone pairs of electrons, that changes the shape or the molecular geometry of the molecule. Now you can also say things about the angles in the electron geometry. Talk more about that in Chem 1. What I want you to focus on for this chapter, and actually for your lab on Lewis dot structures, is being able to write a Lewis dot structure. From the Lewis dot structure, determine this Vesper shorthand notation using this AXE format, and then being able to look at this chart from the Vesper notation, determine what the appropriate molecular geometry or shape of the molecule is. So I really recommend that you have a copy of this with you along with your periodic table when taking your Unit 3 exam, but also when doing the example problems that we will do in the next video.